Flight Director to all stations. Initiate launch protocol for Cambridge 9709, the circle equation. Telemetry is officially live. Look, we are looking at a seriously high-stakes deployment today. I'm sitting here at the central console, and I am seeing multiple student candidates, smart candidates, getting stranded in low orbit. Why? Because their coordinate geometry engines are completely failing mid-flight. Our launch propulsion meter right now, it's currently reading baseline marks across the board. Just average, safe, middle-of-the-pack bands. And we absolutely need to push that into the maximum A-star threshold before your exam clock runs out. So welcome to Mission Control. I'm your flight director, and today we are going to treat the Cambridge AS and A-level syllabus as a critical high-risk flight path. There is literally zero margin for error here. If you want to clear the atmospheric drag of those average grades, you need perfect structural precision. You can't just guess your way into space. So lock in at your stations, double-check your harnesses, and let's initiate this launch sequence to stabilize your mathematical orbit.
Target orbit profile is confirmed. Here is our flight plan for today's mission. Phase 1, the circle equation trap. Phase 2, decoding objectives. Phase 3, the method mark strategy. Phase 4, deconstruct, solve, evaluate. Phase 5, top examiner warnings. And finally, Phase 6, the final exam checklist. Sequence locked. Let's move.
Phase 1, the circle equation trap. We need to talk about this massive disconnect happening right now.
Okay, we have an incoming critical error log straight from the Cambridge Principal Examiner telemetry. And it reads exactly like this. Coordinate geometry is one of the most misunderstood areas in mathematics. Now you might be wondering, how is that even possible? It's just shapes and graphs, right? Well, I've got Alex, my lead propulsion engineer, in my ear right now. He's looking at the raw candidate fuel logs from the last exam series, and he's telling me it is a complete system failure across the board. He's saying that candidates totally know what a circle is, they know what a line is, but they are burning all their time and energy on basic, low-level memorization. They're basically spinning their tires on the launch pad. On the other side, I'm getting a report from Sam, my navigation specialist. She's tracking the layout grid, and she's seeing the exact same thing, just from a different angle. She says candidates are steering the flight incredibly fast, like way too fast. They see a circle equation and they try to jump straight to the final answer without plotting the route. But the absolute second the problem demands multi-stage analysis, the second they have to actually link concepts together, their structural coordinates completely fail. The entire ship comes apart. So listen to me. The atmospheric limit you're hitting here isn't a lack of basic knowledge. It is your execution. When an exam question requires linking 2, 3, or 4 different mathematical concepts together, candidates freeze up. They lose all their upward thrust because they simply don't have a systematic approach to these multi-stage problems. They panic. I've told Alex to pull up the raw fuel data for the baseline equation, and Sam is preparing to map the constraints. We are absolutely not going to let you crash on something this foundational.
All right, raw data is deployed on the main screen. Here's your standard coordinate geometry circle equation. X minus a all squared plus y minus b all squared equals r squared. The center is AB, and r is the radius. Simple enough, right? Alex is telling me the fuel tanks are full, we know the formula, so we should be ready to ignite. But hold on, Sam is actively overriding him on the comms. She's saying, negative. If you just dump that raw definition into the exam paper, you are going to trigger a trajectory failure. And she is exactly right. You are completely ignoring the structural boundary coordinates if you do that. The command words in these high-tier Cambridge questions demand way more than just stating a formula you memorized. The formula itself, it's just the raw propulsion fuel. You literally cannot treat it as an abstract piece of math and expect to break orbit. This entire conceptual framework strictly demands systematic, evidence-based reasoning. When the examiner puts this specific equation into play on page 6 of your paper, your brain cannot just think, oh, nice, a circle. No. It has to trigger an immediate, systematic analysis sequence. You have to ask yourself, do I need to complete the square to extract the center? Am I calculating the radius from intersecting tangents? What is the logical flight path here? You have to prove you're working every single step of the way. If you just wildly plug numbers in without establishing that logical flight path, your launch will fail, every single time.
Moving to Phase 2, decoding assessment objectives. Let's break down these cognitive domains.
I want all stations, everyone watching this right now, to look closely at the scaling expectations on our cognitive domains monitor. We absolutely need to trace exactly how Cambridge categorizes your flight data. Alex is pointing out the low-altitude baseline here, knowledge and understanding. That is just recalling core principles. It's knowing the formula we just talked about. And frankly, that barely gets us off the launch pad. You won't fail, but you aren't getting an A. To actually gain altitude, Sam's navigation data shows we need application. Now, application means extracting data from the text, looking at the scenario, and selecting the right framework. You realize you need to find a gradient, so you apply the y2 minus y1 over x2 minus x1 formula. That gets us safely through the stratosphere, sure, but it is still not the high propulsion A-star orbit we're aiming for today. So what is? The high propulsion orbit is analysis. This is the elite domain. This is where the top 5% of candidates live. You must interpret geometric relationships and actively evaluate the data in front of you. Let's really analyze the difference between a low-altitude descriptive trajectory and a high-propulsion evaluative launch pathway. Imagine a question with the command word show that. If you just calculate some numbers and stop, without writing a concluding statement, you've completely misinterpreted the command word. And guess what? That triggers an immediate system failure alert on the examiner's marking dashboard. You don't get the marks. To hit that analytical orbit, you have to prove why the line is a tangent by, say, showing the discriminant equals 0, and then, this is the crucial part, you have to state the conclusion explicitly. Since b squared minus 4ac equals 0, there is only one point of intersection, therefore the line is a tangent. Boom. That is how you reach the analytical orbit. You do not just describe the math, you evaluate the relationship.
Phase 3. The method mark strategy. The logical process matters more than you think.
We are officially under strict simulated clock pressure right now. I'm monitoring a massive debate happening on the comms between my two pilots. I'm looking at the standard processing sequence on the main display. Identify elements, apply principles, execute analysis, verify results, present format. Now, Alex is arguing that we should overload the writing blocks with textbook definition streams. He's saying, look, if we just dump all the geometric principles onto the page, the examiner has to give us method marks, right? But Sam is completely losing it on the other line. She's saying, are you out of your mind? We are going to burn through our time fuel before we even reach the final calculation. She wants to steer the layout incredibly fast. She's arguing we should skip the basic element identification entirely and jump straight to executing the analysis to establish a direct analytical logic string. She wants those high-tier marking bands instantly. But Alex snaps back, if you skip the principles, Sam, you lose the foundational method marks. What if your final calculation is off by a single decimal? You'll crash the entire response and get 0. And Sam shoots back, and if you write a novel for a 4-mark question, the clock fuel hits 0 before we even open the next page of the exam. Okay, I'm cutting their feeds. Stand down, both of you. Listen to me, because they are both risking a total mission failure right now. Alex, dumping raw definitions burns way too much of your time energy. Sam, rushing to the final answer, ignores the structural limits and removes your safety net. The examiner heavily rewards the logical process. You must follow the sequence precisely. Identify the elements quickly in your head, state the applied principle with a single precise line of algebraic notation, execute the algebra flawlessly, and present the final format clearly exactly as requested. The method marks are secured by the crystal clear transparency of your logic, not by the sheer volume of your ink. We balance the fuel budget by being mathematically concise but logically complete. That is the sweet spot.
Entering Phase 4. Deconstruct, solve, evaluate. This is your ultimate problem-solving framework. All right, let's run a live text engineering simulation right here, right now. Imagine we are staring down a brutal, multi-part coordinate geometry question. It's an 8-marker, it's intimidating. So how do we tackle it without spinning out of control? Alex is initiating the first step, deconstruct. He's calmly extracting the equations of the line and the circle from a huge block of confusing text. He's isolating the variables. Good. Now Sam is jumping in for the second step, solve. She's substituting the linear equation into the circle equation to find the points of intersection. She's expanding the brackets, she's grouping the x squared terms, the x terms, the constants. The algebra's getting really messy, but she's pushing through, throwing it into the quadratic formula to get the roots. But wait. Suddenly, alarms are going off on the telemetry console. The roots are throwing up complex numbers on the calculator. The discriminant, that b squared minus 4ac, is a negative number. Alex is yelling that we've got a massive system anomaly. Sam is panicking, saying, forget the anomaly, just write down some numbers, pretend it worked, and let's finish the paper. Negative. I'm overriding them. This is exactly why our 3-step assembly line exists. Deconstruct, solve, evaluate. You hit a negative discriminant in the solve phase, do not force an impossible calculation. You don't try to break the laws of mathematics to get a final coordinate. Instead, you calmly move to the third step, the evaluate phase. What does a negative discriminant actually mean in the geometry of this specific problem? It means the linear path and the circular path do not cross. The line and the circle do not intersect, period. That is your mathematically justified recommendation. When you face a daunting question in the exam hall and the data looks completely wrong, do not panic. Run it through this framework. Evaluate the results for reasonableness. If the numbers mathematically prove that the line misses the circle, trust your telemetry. State it clearly to secure those analysis marks. You write, since discriminant is less than 0, there are no real roots, therefore the line does not intersect the circle. You just turned a moment of sheer panic into a maximum mark evaluation.
Launch trajectory hold. Before we deploy this top-band paragraph structure to clear orbit and look at comparative analysis, we need to optimize your educational flight deck. Take a second right now, literally, just hit pause if you need to, and subscribe to Ace the Exams at the handle @AceTheExams. Enable all notifications, hitting that bell icon so it lights up bright yellow on your HUD. You want to make sure you never miss our weekly flight-tested exam hacks, whether you are launching your academic career at IGCSE, O-levels, or the advanced AS and A levels. All right, back to the simulation. Oh no, Alex is reporting an unexpected structural data loss mid-paragraph. Our evidence links are suddenly dropping on the main display. We are losing the comparative connectives. Sam is warning that the entire mission is going to terminate because the candidate isn't identifying the similarities or the differences in the geometric shapes. Okay, I'm manually overriding the console now. I am deploying the structural power-up framework. We are going to stabilize this text flow live using proper analytical structure. Watch how we do this. First, state the point clearly. The gradients of the two radii are different. Next, provide the hard mathematical evidence. M1 is 2, M2 is -1/2. Then explain the link between them using a comparative connective. Because M1 multiplied by M2 equals -1, the lines are mathematically perpendicular. Finally, draw the relative conclusion to lock in the marks. Therefore, the tangents form a perfect right-angled intersection. Boom. Orbit stabilized. That is exactly how you rebuild a high-scoring block of text under intense exam room pressure.
Phase 5. Top 3 examiner warnings. We need to avoid these at all costs.
I am officially handing control over to you, the audience, for a live radar check challenge. We call this the Visual Radar Sweep. Alex is initiating a strict 60-second visual countdown timer on the main display right now. Can you feel that pressure? Good. I want you to look at the top 3 examiner mistakes logged heavily in our system. Number 1, wrong approach for the context. Number 2, forgetting to check format and presentation. Number 3, answers are not specific to the context. I want you to scan your own past paper memories. Think back to your last mock exam. Spot the logical malfunction in your previous work before this timer resets. Sam is in my ear, giving us the 10-second warning. She's saying, "Director, they usually forget the context. They do all the math, calculate the radius perfectly, but completely forget that the word problem asked for the total diameter of a Ferris wheel, not just the mathematical radius of a generic circle." And time is up. Digital Indicator is highlighting the massive discrepancies now. If you don't check your format and presentation, like let's say you leave your answers in messy decimals when the question explicitly requested exact surds, you will hemorrhage critical marks. But the biggest, most dangerous trap of all is context. Elite examiner logic dictates that math without context is just meaningless noise. You have to anchor your numbers to reality.
Alex just flagged a failed attempt on the radar. Generic answer telemetry is coming in. Look at this. The candidate just wrote, the gradient of the radius is perpendicular to the tangent, y minus y1 equals m times x minus x1. Okay, sure, it's technically a true statement, it's a real formula, but they aren't actually solving the puzzle in front of them. The system failure alarm is literally screaming. They've left the math completely abstract. Now Sam is routing a completely different trajectory to the main screen. She has the precise, context-specific answer locked in. Let's read it. Using the center coordinates 3, -2, the gradient of the radius is calculated as 1/3. Therefore, the perpendicular gradient of the tangent exactly at point A is -3. The final equation is y minus 4 equals -3 times x minus 5. Look at that. The propulsion meter is absolutely peaking right now. That right there is the fundamental difference between an aborted launch, where you get maybe 1 pity mark, and clearing orbit with full A-star marks. You must rigorously link every single coordinate, every single calculation, and every single gradient directly back to the specific numbers and the specific scenario provided on that exam page. No generic fluff.
Final phase? Phase 6, the final exam checklist. This is your ultimate pre-flight toolkit.
Alex is confirming that all systems across the board are flashing green. We have successfully extracted the required data from the dense text and tables. No variables left behind. Sam on navigation confirms we actively interpreted the complex geometric relationships instead of just guessing them, and we executed the heavy algebra with clear, undeniable notation that any examiner could read easily. And most importantly, Alex verifies that we strictly, without fail, linked our final numerical answer directly back to the original scenario. Our propulsion meters are officially peaking at a sustained maximum A-star reading. Excellent work today, crew. We have reached the summit. So let's distill this entire high-intensity session into the 3 universal rules of engagement you need to memorize. Number 1, the 3-step question scan. You must always deconstruct the data first before you start writing blindly. Number 2, the fuel budget allocation. You have to aggressively manage your time so you can clearly show your method marks without having to rush the deep analysis at the end of the paper. And rule number 3, the post-launch system review checklist. Do not flip the page until you verify your final format and ensure your answer makes contextual sense. Follow these 3 rules, and your flight through coordinate geometry will be absolutely flawless.
All right, we are officially closing this launch simulation. I need all crew members, every single one of you watching this right now, to lock in your final protocols. I have a very serious question for you, and I want you to be honest with yourself. When you sit down with a stack of past papers tonight, are you just blindly practicing to find the right answer in the back of the book, or are you actually executing the perfect evaluative method that we discussed today? Think about it. Master the method, and I promise you, the marks will follow effortlessly. Now, before you power down your command stations for the day, you need to subscribe to Ace the Exams at the handle @AceTheExams. Click that notification bell right now to lock in your radar for our weekly grade masterclasses. And finally, I need you to drop a comment below sharing exactly which Cambridge subject and level, whether that's IGCSE, O-Level, AS, or A-Level, you are preparing to conquer next. Let us know your coordinates so we can build the right flight path for you. Stay sharp, trust the telemetry, trust your training, and I will see you in our next masterclass launch. Flight Director, signing off.